All right, you guys, technical difficulty, but I'm back. So this week's segment, this recording is going to be in 2 segments. Hopefully there's no more. Okay, so we were talking about the bicyclist. Since I'm not exactly sure where we ended, the bicyclist has a velocity of positive 6 meters per second and an acceleration of positive 2 meters per second squared. We want to know where she'll be 1 second later and then where she'll be 2 seconds later, okay? So 1 second later, she will have gone from 6 meters per second to 8 meters per second because she is increasing her speed, her velocity, by positive 2 meters every second, okay? So 1 second later, her velocity is going to be equal to positive 8 meters per second. So 2 seconds later after this initial time would be 1 more second after this, which means that her velocity will have increased by another 2 meters in that second. So 2 seconds later, her velocity will be positive 10 meters per second. So 1 second later, it would be positive 8 meters per second. 2 seconds later, it would be positive 10 meters per second. Okay? Now we have our bicyclist. Again, okay? We're going to change some information about her, all right? Now, she is going negative 6 meters per second, okay? She's going negative 6 meters per second. And her acceleration is positive 2 meters per second squared, okay? So she's going negative 6 meters per second, and her acceleration is positive 2 meters per second squared. So what will her velocity be 1 second later? Well, 1 second later, her velocity will have increased by positive 2 meters per second, which means that her velocity will be negative 4 meters per second, okay? Now, 1 more second later, her velocity will have increased by another 2 meters, making her velocity negative 2 meters per second, okay? So 1 second later, it'll be negative 4 meters per second, and another second later, it'll be negative 2 meters per second. Time to go on to another example. All right, this one is called running the court. We've got a basketball player, and he's starting to the left end of the court, okay? And he's going to move with the velocity shown. We're about to draw a graph together. Okay, so remember, if I draw it, you draw it, okay? And if you're like, Mrs. Bernal, there's a glare. I can't see anything you're doing on the board. I uploaded a PDF of your notes too, okay? I got you covered. So we've got this velocity versus time graph, all right? And we're gonna go 3, 6, 9, 12 on our time axis. And we're gonna go -3, -6, and then this way we'll have 3 and 6, all right? At 0 seconds, we're at position 0. At 6 seconds, we have reached position, a velocity of 6 meters per second. And at 12 seconds, we will have reached -6 meters per second, all right? So there is our graph, okay? Now it's crossing the time axis at t equals 9, okay? So it is crossing there. Now, we want to know what is his acceleration from t equals 0 to t equals 6, and from t equals 6 to t equals 12, okay? So let's start with from t equals 0 to t equals 6. So we're going to be dealing with this portion of the graph right here, okay? So we want the slope of this line, right? Okay, so acceleration is equal to delta v over delta t, and that's our rise over our run. So he's ending at 6 meters per second. He started at 0 meters per second, and he's ending at 6 seconds and started at 0 seconds. So we're going to end up having 6 divided by 6. And what 6 divided by 6 gives us is an acceleration of 1 meter per second squared. Okay? So from time t equals 0 to time t equals 6, he is going to have an acceleration of 1 meter per second squared. Okay, now we need to look at the time period from 6 to 12, okay? So from 6 to 12, we're going to have that his acceleration is once again equal to delta v over delta t, right? Okay, so he ends at negative 6 meters per second and started at 6. So we're going to have negative 6 minus 6 on top for our delta v. And then for our delta t, he ends at 12 seconds and started at 6. So we're going to have 12 minus 6. That's going to give us negative 12 divided by 6. And if we do negative 12 divided by 6, what do we get? You should have said negative 2 meters per second squared, okay? So his acceleration from 6 seconds to 12 seconds is going to be negative 2 meters per second squared. And yes, you can have negative acceleration. Negative acceleration means that your acceleration is working against the direction you're going in, okay? So it's like you're slowing yourself down instead of speeding up. All right, what we want to do now that we have this information is we actually want to draw the acceleration versus time graph of this graph, okay? So we know that the acceleration here in this segment is 1 meter per second squared. And we know that for the other segment, it's negative 2 meters per second squared. So I'm going to go ahead and erase all this work so we can draw the new graph. Okay, new graph time, right? Now we are drawing together our first acceleration versus time graph. This is so exciting. Okay, so we can just go 1, 2, negative 1, negative 2, and then we're still going to have 3, 6, 9, 12, because our time hasn't changed. What's changed is that our acceleration doesn't go really as high as our velocity does. So our acceleration graph is going to look like this. From 0 to 6 seconds, it's going to be a straight line, okay? At 1 meter per second squared. Then from 6 to 12, it's going to be a straight line at negative 2 meters per second squared. And then we'll draw our handy dandy trusty dotted line to sort of connect them in our step graph, okay? So, is the acceleration constant for each segment? Yes, it is, okay? We have a constant acceleration for each segment. And our linear lines sort of tell us that, right? We can tell that it's constant. Okay, well, we're done with that. So let's move along. Move along like I know you do. Move along. Any All-American Reject fans in the house? Right? Move along? No? Okay, so this is where stuff gets really exciting, you guys. the kinematic equations of constant acceleration. So let's get down to business, all right? The kinematic equations of constant acceleration. So exciting. I love these, you guys. All right, so consider an object that has constant acceleration, all right? And it's during an interval. Let's say that our interval is from, it's delta x equals xf minus x naught. That's the interval we have, and we have constant acceleration over that interval. And at t naught, its velocity is going to be v naught, okay? And at tf, its velocity is going to be vf. So at our initial time, we have our initial velocity. At our final time, we have our final velocity. So the velocity is changing because it has acceleration. So if we don't have acceleration, our velocity doesn't change, it stays constant. But if we do have acceleration, our velocity is going to change, all right? So if we look at these graphs, we're going to have an acceleration versus time graph. And what we're going to see here is that from T naught to TF, okay, that's the area we're focusing on. And let's say, we'll just call this A, all right? At A acceleration, it's just going to be constant. And from our T naught to TF is going to be a delta T for us, okay? Now, we're going to have a T naught and a TF. And what we're going to see here is that this is going to be our initial velocity, our v naught, and here would be our final velocity, or our vf. So this graph goes with this graph, all right? The slope of velocity gives us the acceleration graph. However, displacement, our position, as we've learned, is the area under the curve of the velocity graph, right? Displacement is the area under the curve, okay? So let's go back to an equation we've already known. Okay, so now we see how all of our graphs connect. And you know how we just learned that acceleration is equal to the change in velocity over the change in time, and that's equal to the final velocity minus the initial velocity over the final time minus the initial time? Well, we're going to rearrange this equation for VF. So like, let's say we're given information and we want to know what the final velocity is. We want to know what this is, okay? Well, we're going to have that A equals VF minus V naught over TF minus T naught. We're going to multiply both sides by T final minus T initial. So we're going to have A T final minus T initial is equal to VF minus V naught. And then finally, we just have to add over this V naught. So we'll end up with that VF is equal to V naught plus A delta T, because remember, this can be written as delta T, all right? This is one of our very first kinematic equations, all right? final velocity is equal to initial velocity plus acceleration times our change in time. This is our very first kinematic equation. We just derived it from our equation for average acceleration, okay? Any questions so far? I'm just kidding. You guys can ask questions. This is a recording. Okay. So, we previously learned that our final position is going to be equal to our initial position plus the area under the curve of a what graph? Of a velocity versus time graph. Okay? So, if we think about it, we can break up things into triangles and rectangles, right? So like, for instance, if we had that same graph that we had over here, and we wanted to evaluate it from T naught to TF, we could break it up into a triangle and a rectangle, couldn't we? And then we could use the shapes to our advantage. We already know how to find those areas, right? Well, the area of a triangle is just going to be V times delta T, okay? So velocity times our change in time. Sorry, guys. Area of a rectangle. I thought that looked wrong, and I'm glad I second-guessed myself. The area of our rectangle is just going to be our velocity times our change in time. The area of our triangle is going to be 1/2 acceleration times delta T times delta T. And what that simplifies down into is 1/2 A delta T squared, okay? This is going somewhere, I promise. You guys get the pleasure of deriving equations in this class, all right? So we have the area of our rectangle, what the area of our triangle would be. So when we have that equation of xf equals x naught plus that area under the curve, we can now write it as xf equals x naught plus our v naught delta t plus 1/2 A delta T squared. This is kinematic equation number 2, all right? Final position is equal to the initial position plus the initial velocity times our change in time plus 1/2 our acceleration times our change in time squared, okay? So that's kinematic equation number 2. Another way you'll see this written a lot is that someone will have already subtracted that x naught over, and they might just have it written as delta x equals v naught delta t plus 1/2 A delta t squared. Okay, so they might just have the delta x over there because they already ripped out the x naught, okay? So we have one more kinematic equation left to go, okay? One more kinematic equation to derive. Part of the fun of AP Physics C is you get to derive everything. Okay, so if we were to solve VF equals V naught plus A delta T, you know, that very first kinematic equation we derived. If we were to solve it for delta T, okay, we would get that delta T equals VF minus V naught over A. All right, what we can do is plug this into that equation we just got, okay? When we plug this into that equation we just found, we get that XF is equal to X naught plus V naught times VF minus V naught over A plus 1/2 VF minus V naught over A squared. Don't worry, I'm not going to say, this is your third kinematic equation. I can simplify it. And what it simplifies down to is VF squared equals V naught squared plus 2A delta X. So that is going to be our third and final kinematic equation, all right? Our final velocity squared is equal to our initial velocity squared plus 2 acceleration change in position, all right, our displacement.